All right, so back to the question. We had a question. Somebody have a question from Lauren?
Yes, Danielle does.
Yeah, I had a couple of them.
Everything she said.
You said one PPG.
I know. I don't want to know.
5.1,
Yeah.
39.
Oh, okay. The one about the club.
Sure.
5.1, the one with the N of P.
I don't know. I didn't even write it down. I was like, I don't know how to do that, so I'm gonna stick it.
So it's 39 on page, on section 5.1, right?
Yeah. Yeah.
Okay. So it says a number of ways in which a president, vice president, and treasurer can be elected can be determined using this. Where P is the number of people in the group, right? So 39 says if you have 20 people, right? You have 20 members, in how many ways, how many ways can you elect president, vice president, treasurer? And really, this boils down to how many ways can you select 3 people out of 20, and then rearrange those 3 people, because you could have Sam, Bill, and Barbara, right? And then you can rearrange them because then Sam could be president, blah blah, or Barbara could be president, blah blah, or Bill, whatever the other guy was. So, do you have to know all that? No, really, what this really boils down to, here's a function. Where's 20 go? Yeah, because it's the number of people you got. Throw a 20 in and see what it comes out to be. That's it. The thing you guys maybe don't realize right now is there are a ton of these kind of functions floating around. I mean, they're all over the damn place. You just don't see them all the time because they're not used all the time. But this is true. If you throw in a number for P, it will tell you the number of ways to choose 3 people out of that. That's kind of funky. If you think about it, it's kind of funky. But is it immediately applicable to us in everyday life? No. But it's nifty that it's out there, and all I got to do is throw a number in, and it spits out the number that I want.
So is that formula useful for any kind of thing like that?
Yeah, yeah.
So that's like a set formula for determining.
Now, what it turns out to be is there's a more general idea than just creating a polynomial for this, because this is specifically for picking 3 people from a group of people.
Okay.
What if I want to pick 5, 7? Do I develop a brand new formula for each one? Or is there a bigger idea that can come? There's actually a bigger idea, right? But if all you ever have to do is pick 3 people from a group of people, this is beautiful, right? So all you have to do now is throw a 20 in. It's going to come out to be larger than you might think, but this 20 cubed gets pretty quickly big, right? It's always larger than you realize. Have you guys ever heard I can't remember exactly how it goes, but if you allow like 14 toppings on a pizza and you can have as many of them or as few of them or any combination of them, how many different pieces can you create? It's in the millions. People are always like, what? I thought it'd be like 30. No. All the possible combinations grow really quickly. Let's see. I think sometimes that might happen to a few guys. If they give you a function, they start to explain the idea behind the function. Don't get too wrapped up in the idea. I mean, obviously, I'm big into the idea because it's good to know what it's useful for. But for you right now, you're just trying to plug and chug. Make sure you understand what it is. Make sure you know where the number goes, and then chug it out, right? And then maybe step back and go, "That's kind of cool. That exists." Next problem. Keep going. Hopefully they're moving down the building. I obviously had to request this room, so I wish they would have told me, oh, by the way, Jeff, just before you move everybody, there is gonna be a lot of stamping around going on.
Just after.
They didn't say a word about that. Well, thanks, guys. Thanks for the warning.
I don't mind.
I don't think you speak for the group, that's all.
I don't mind.
You work for a public school system, they gave it to you easily, you should have known right away.
Yeah, you're right. I should have realized there was something wrong. So any other questions from homework? Yeah. Sure.
I forgot to give you the second page.
Oh. Okay. All right. So let me do this. Did I ask you? Okay. Gotcha. Okay. Anything else from the homework? Forgotten page. Sounds like a really freaky movie. Forgotten page. Okay, nothing else, okay. And again, I'm an optimistic fool, so I'm going to take that to mean that everything's going wonderfully.
Absolutely.
Good. So just a reminder, if you're getting behind in homework, or if you've been behind in homework and haven't told me, tell me, come see me. And I can try to either cut back. I've been letting a few people do the reviews instead of every section. I don't like making that a blanket thing because if you're able to keep up, you need the practice, right? But if you're getting behind, then you're screwing yourself over in the later sections. So I want to give you practice and get you quicker through it. So come see me if you're getting behind on the homework. So if there's no other questions, we're going to kind of get back into 6.1. We already discussed the main ideas, and to tell you honestly, we've already got the main ideas down. We just have to do some more examples. Just to kind of remind you guys, if you don't know factoring, you can't do chapter 6. So if you're not good with factoring, focus all your energy on 5 right now.
How about domains and functions? I mean, not functions, but domains.
Domain, okay. And that's going to come in big in the beginning area of chapter 6 because they talk about these expressions that have variable stuff on the bottom. Right, so I can ask you, what's the domain of this thing? And the funky thing is we've already done this problem, really, right? We've done an easier version of this problem like this. What's the domain of this? X cannot be 1. Please don't write x equals 1 for the domain because then you're telling me that's the only thing I'm allowed to use. The domain is everything I'm allowed to use. And a good way to answer that is, well, you can't use this, which means you can use every other thing, right? So what's wrong with that? Why is that harder? Yeah, I got to factor it out so I can see the pieces, so it's just as easy as this was. Why was this 1? Because 1 minus 1 is 0. So if I can just break that down into parts, can I? No, now you can. So how do you factor that now that I got the right side of it? I like it. Cool. And then what are the 2 things that I have to throw out? I like it. Be really careful. Some of you guys are just you're putting this down and you're getting it straight from here, and then you say, well, why the hell would the sign change? Because what you're really doing is you're saying, this can't be 0. How do you solve that? Well, you set each one to 0, and then you have to add it over, so that's why the sign changes. So be careful about that. I see a few people just writing it straight from here to here, just not even changing the sign, but -6 would not make this 0. 6 makes it 0. Yeah.
And are they going to have that interval notation stuff that you need to use that in chapter 7?
In 7, we're going to be doing radical expressions. So we're in 6 right now. So 6 we're going to do.
I mean, did I say 7?
Yeah. Okay. 6, I personally am okay with you writing it. Yeah, they don't really make a big deal out of it. I'm okay with you writing it like this. That's fine.
Okay.
Yeah. Because the interval notation here doesn't really help. I mean, here's what it would look like. You're like, okay, how does that tell me more or better than that? Really? They both mean the same thing. Is 5 in this? Where's 5 in that? This says don't include 5 and then start over at not including 5. So there is no 5 in here, is there? You guys see that? This here, I think of this whole little piece like skip. Starting at infinity, skip 5, skip 6, go to infinity, right? So 5.5 is in here, isn't it? It's in that one. 7's over there. 6, not in anything. It's not in there at all. So these mean the same thing. 5 and 6 excluded, 5 and 6 excluded. Which one gets more to the point? This one, so screw that. Yeah. Okay. All right. Let me see. Blah, 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 blah. Okay. So there's going to be some domain questions, and then you're going to jump into the real heart of this section, which is reducing rational expressions. Yay. So something like this here. I think that'll work. We'll find out. Yep. Okay. Now, what did we say the other day that you gotta be real careful about that? It's so freaking easy. Okay, how much you understand what I'm saying, it's so easy to just do it. You start going, well, x cubed divided by x squared, that leaves an x here, you start reducing.
Can't do that.
Tell me real quick why that won't work.
Because of plus or minus, it's not multiplication.
Exactly. Division can only cancel out multiplication. They can't do a damn thing with the minuses and pluses. Right? Division can only cancel. So that's like this idea here. I cannot do anything with this really directly. I could break it up, but that's not really direct. But I can do something with this. Because division cancels out multiplication. Okay, so what do I have to do first then? Yeah, if I factor, I bring in the operation of multiplication, right? I make it something times something, and then maybe I can kill something with that division bar. So how do you factor the top? What form is that in? Cubes. I like it. So little dude, big dude. This is XXX. This is 3, 3, 3. What's the little dude look like now?
X minus 3.
I like it. One of these X's minus one of these 3's. Those two X's go
Squared.
here. Those two 3's at the end there. And what's the middle term going to be?
Plus
Oh,
3.
yeah.
I like it. Opposite sign, 3 times x. Once you see that, how it goes together, and I desperately try to make it make sense why those things are needed to make it work, every damn cube is then the same problem. So start looking at it like that, like all cubes are easy. Once you get the process, you don't have to change it. It's always the same. If it's a cube, it works this way, period. What can you do on the bottom?
Divide by 3.
Thank God. Don't do 3 times 27. 2 reasons. Because you can take a 3 out, that would be too long, and it's never going to factor. What did I say the other day about a trinomial when there's a cube in there? That trinomial might eventually become the big dude, and you can't factor the big dude. So definitely look for that GCF. So 3 comes out, what are you left with?
X squared plus 3.
Yeah, so it cancels, obviously. The big dude cancels. So what are you left with?
X minus 3 over 3.
And then you kill the 3?
Nope.
Good. All right, don't do that, please. You can't, because again, division cannot cancel that subtraction. You have to add 3 to cancel the minus 3. You can't divide 3 to cancel the minus 3.
That was 3x.
Yeah, exactly. If it was 3 times x instead of x minus 3, I like it. Yeah. If it was multiplication, you could do it. Okay, and let me show you something on the side here. I showed you this kind of thing before when we started factoring, but that problem's done, right? It's done. That problem's done. X could be anything, right? Let's make x equal to, I don't know. Let's make x equal to 2. Why not? Remember we did this before? Because I want to show you what you're doing. Whenever you do something with expressions, you're doing an infinite number of numbers. Because what can those expressions represent?
Right.
Any number, really, right? So what if x is 2? What do I get on the top? I get 2 cubed minus 27. Yeah, I get 8 minus 27.
19.
Negative 19.
Negative.
And on the bottom, I'll get 3 times 2 squared, which is 4, plus 9 times 2. Is everybody cool with that? I have to make this point over and over. Trust me on this. You're never going to have to do this. This problem's done. You don't have to do this. This is a little side thing I'm doing. What do you get on the bottom now? You're going to get 12 plus 18. It's 30 plus, 57. Believe it or not, that reduces. 20 times 3 is 60. 19 times 3, therefore, is 3 less. It's 57. So that's negative 1/3. So when you plug a 2 in, this expression is this. And it reduces to this. But what did we do here? We reduced that expression. So that better be the same as that. X was 2. What do you get when you do this? 2 minus 3 over 3. Negative 1 freaking thirds. Right? So anything you plug in for X, unless it makes the bottom 0, obviously, right? If it makes the bottom 0, all bets are off. You can't use that X. But any X you plug in, you can do a very similar thing. Cool? Okay, so that's what you're really doing, yeah.
And the expression, the difference between an expression and an equation is that the equation has an equal sign.
I like
it.
it.
Equals
This is a rational expression because that equals was one I brought in, just to show what I'm doing with that expression. There's no equation to begin with. You can't end up with, because you're right, I like it. Everybody always says, okay, equals 0, so X is 3. Yeah. No. It's not an equation. You have to end with an expression with X. Yeah,
Okay.
I like it. Cool. Okay. And really, all they do from there is they just throw more shit at you. They throw more factoring methods at you. They do a fraction divided by a fraction, and you flip that guy, of course, and you factor and kill. It's the same idea. Factor, kill. Right? Sounds like a very boring PlayStation game. Factor, kill. So what I mean is, here's probably, let me give you the ugliest problem maybe you would see. Ooh, that's nice. I like that. Ooh, that's even uglier than I want to go. Let's go there. Yeah. Look at this problem. Here's why you don't care how long this stupid thing is. All this crap, the only ones you care about are what you can factor, and a little extra thing now is what's dividing, because of course, what do you have to do with that piece? Flip it, and then it's the same as multiplication, right? If you forget to flip it, you won't have the right stuff kind of trying to cancel, so you gotta be careful. So let's try to do both of those things at once. I mean, what in here can I factor? I can factor this, right? And this. I can factor this and this. The easiest factoring there is GCF there, right? Can I factor these? Maybe, but again, do I have any cubes in here?
Yes.
Yes, so maybe that guy's going to be the big dude for this guy. So let me hold off on trying to factor anything over there. This one I might be able to factor because there's no cube up top, right? So let me try to show you the hints that problems give you as you do them. These are easily factorable. I've just got a factor. There's nothing I can really do besides it. What do you get on the top here? Beautiful. I love it. Plus 3y. I like it. So the whole idea of the difference of squares is minus plus. So the middle term cancels, right? You guys take a minute and try to do the bottom. I'll get you started. Little dude, big dude.
2x.
Hold up. Alright, so now help me out here. The little dude will look like
2x minus 3y.
2x, good, minus
3y.
3y.
What x squared?
4x squared, I like it.
Plus 6xy.
I like it, so let me go there. 9x squared. The middle term will be plus
6xy.
6xy. That looks very familiar. As promised. It's not always going to happen, but I bet you if there's a cube in there and there's a trinomial, there's a very good chance they'll cancel each other out. Big dude, right? Now let's try this. I'm going to reciprocate it, right? But can we handle it if I at the same time, what comes out of here? 3, and what's left inside? Is everybody cool? I'm flipping this because it's divided by. What comes out of the top? 2.
Plus 3y.
That was interesting. That looks, well, not quite. They almost got it. That didn't go away, did it? What will it do?
It went away from the top. Oh, no, never mind.
So the signs don't change when you flip it?
No, right? The signs definitely don't change when you flip it. It's just dividing by a fraction is multiplying by the reciprocal. Right? And we actually know that inherently. Dividing by 2 is cutting something in half, right? So division by 2 is multiplication by 1 over 2. We kind of already inherently know that they mean the same thing. So when I divide by a fraction, I multiply by its reciprocal. Now over here, I'm not going to try to do crap with that dude for 2 reasons. He's going to die, and I see now that he's a big dude that I wouldn't be able to factor anyway, right? So why mess with him when he's dead, peace walking? I don't know what you Now the bottom, though, can you guys see why I don't have to worry about the top? It's pretty obvious because it's going to go away. So who cares about the top anymore? But I've got to worry about the bottom. There's nothing for him to go with on the top here. Right? There's nothing for this guy to cancel with. So maybe I can factor him and then pieces would cancel. So let's take a second look here what I got. What dies here? What goes away? So that's gone. That's gone. Anything else? Yeah, these are gone. So here's that thing I was talking about, the hint that the problem gives you sometimes. Who could tell me what is a really possible to be a factor of this?
X minus 3.
Exactly, right? Can you guys see that? It might not be. Maybe it won't cancel. If it doesn't work, then you go, screw it, I'll just try to factor this, and you know. But the only reason I would have to factor this is if a piece would cancel with that. Isn't that the only thing left alive on the top to, I mean, I know it's a 3, but 3 ain't gonna help me out. This is the only thing that could possibly cancel with that guy. If you don't understand what I'm saying right now, don't look at it that way. Just do 4 times 3 is 12, factors that had to be 8. Attack it like normal. You don't have to do this. This is a shortcut. So if I know that a factor of this is probably that x minus 3y, right, so that it would cancel, what's got to go here to make 4x squared? Careful. 4x. What's got to go here to make 3y squared?
3y.
Because I've already got 3. Do you guys see how I'm getting that? This is already x. So x times 4x is 4x squared. That's why there's a 4x there. This is 3y. So how to make 3y squared? A y. It's got to be positive 3y squared, so doesn't it have to be negative here? Minus 3y times negative y is plus 3y squared. Do I get the right middle term? Minus 12 xy minus 1xy is minus 11. I don't get the right middle term, right? So that's okay though. I tried the easy way. It didn't work. So what does that actually tell me? I don't know if you guys totally wouldn't. We'll do another one like that because it is very useful. That didn't work. Not a problem. Does that mean I even have to worry about factoring this thing at all? I really don't have to worry about factoring because that was the only thing that could have canceled. It's not going to work that way. Screw him. I don't need to factor him. There's no way that something's going to cancel because the only thing that could have doesn't.
So then you just leave it in that.
Just leave it alone. Now if you try to factor this, let's see if it actually works. Factors of 12 that make 8.
6 and 2.
6 and 2. And then they're both negative, so it will work, but the factors, nothing will be able to cancel there.
So just because you could factor it in this instance, you don't have to.
Because I know that the only thing left that
Right, I
could
get
cancel
it.
doesn't. So
Right.
there's no reason to.
I mean, before it was like factor, and now we're saying, well, we.
So again, let me be careful. I'm showing you shortcuts that come out because of the fact that there's other pieces of the problem that might cancel. So there's shortcuts to this thing. If you don't understand the shortcuts, you just take each piece, factor, 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 try to factor, and that's a very straight way to do it. And then if you can factor it, see if something cancels. See if some piece of it dies. I'm trying to show you a few shortcuts so you don't do as much work.
So the reason I ask is, so that would be, we'd put those together and that'd be the answer.
That'd be it.
And that'd be good, factored or unfactored.
So what's left alive here? Let's see. There's a 3 times x minus 3y. Nothing left alive on the bottom, on the top other than that. On the bottom, there's 2 times this thing. I like it. That's as far as it goes. Right? So sort of like if I had a problem like this, 5 over 686. Can you factor the bottom? Can you factor the bottom?
Yeah.
Yes. Would you?
No.
Because you know 5 won't go into any
Okay.
factor of that, right?
Makes sense.
Same thing I'm talking about here. You know that won't go in because the only way it could is if it was a factor, and we already know it's not. It didn't work when I tried to make it a factor. So screw him. I'm not going to factor that. There's no reason. All right. But again, if you didn't understand my shortcut, you can attack each piece. It's good factoring practice. Why the hell not? Right? Just factor, 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 and then cancel. That's as ugly as it's going to get. I mean, as I was writing, I heard you guys groan. You're like, when the hell is he going to stop putting shit up there? But you see, I don't care how much crap, you just factor, 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 and then just look what's on the top, what's the same thing on the bottom, kill it. It's the same idea. I don't care how big I make the problem. It's the same idea. Let me step it back a bit and let you guys try one out on your own.
Hey, Jeff.
Yeah.
This is you with a question. You're teaching statistics next semester? Do you know what time?
Oh, shit. Well, off the top of my head, no.
12 or something.
Something like that.
Yeah.
Okay.
I love stats.
Good, I'll be in your class.
Good. All right.
That's my last one.
I teach at least one stats every semester because except in the summer I couldn't get it. But okay. Try this one. Let's do number. No, it's not terribly ugly. Number 70 looks good.
What page is that?
This is page 451. So try to give you one that wasn't overly heinous, but it has the idea. It's the same idea. All they can do to you is make the factoring more difficult, which you guys are like, well, that's enough, dude. But that's why it's so important to know your factoring forms, know your methods. So this one's not too bad. What form is this in? How do I attack this guy? Squares. So it'll be y.
Minus 6, y plus 6.
I like it. This guy, 16, can be broken down to,
Negative.
Y
I like
minus
it.
4.
It's gonna be 4, 4 to make 8, and they both have to be negative. I love it. I'm gonna flip this dude and factor him at the same time. Is that all right? So I flip him. So the bottom here is up top. So yeah,
Y minus
it's gotta be
4.
3 and 4.
Y plus 3, Y minus 4.
I like it. The bigger one's gotta be negative to make the middle term negative.
And the bottom one is 3.
Beautiful. So this guy's just a GCF.
Y minus.
You said you flipped it.
Yeah. If you divide by a fraction, you have to multiply by its reciprocal. Right? That's how you divide
Creating
fractions.
multiplication.
Exactly. Cool. So that's why I put this up top and this down below, because I'm flipping it. You don't have to do it all in one step, but now is everything factored?
No.
Yes.
Oh, yeah.
Everything's factored. This is this times that. You got a bunch of numbers multiplying by each other. It's a beautiful time for division to step in and do its thing, right? What cancels?
Negative 6.
Yeah, the y minus 6 cancels,
Y minus
and one of these y minus 4s cancel. How's that?
Yep.
So on the top, I'm left with
3.
there you go. So sometimes, it's just like numbers. Sometimes a lot will cancel. Sometimes barely anything or nothing will cancel. You're going to see it all in the homework. I like to do a problem where like almost everything dies. It kind of is satisfying. Get out of here. You're left with y or something.
So is it alright if we write down the problem like for 70 and we just write it out and we just flip it? Like, we just do the multiplication and then just flip the sign instead of writing down the original problem and then writing it again?
Oh yeah, you don't have to write the original
Okay.
problem down when you're doing the work.
Okay,
Yeah, you
we can
just
flip
jump
it
right
and
into
you,
it. Yeah,
okay.
yeah. There's one thing I want to show you. I'm going to try to do this. Well, let's see. I think I should bring the graphic calculator up. If I have this function here, let's see. Let's make it interesting. Can somebody tell me anything about that function? It's written in black, Joe. Yes.
X plus
No, it can be, but
is positive.
cannot be, right?
Cannot be.
So x cannot be what?
4 negative 4.
Careful.
2.
Yeah. 2 or negative 2.
2. No.
Cool. Now, what does that mean graphically, though? X it just simply cannot be plus or minus 2. So very rudimentary, just not even trying to plot points. Just something freaky has got to happen at 2 and negative 2, obviously, right? It can't just do this, hi, because then x can be 2. So at least there's got to be like an open circle there or something freaky, right? But it's even worse than that in a way. And let's see if we can analyze it a little bit before I pull up the graph. Or maybe I'll just try to graph it. Here we go, here. When I get really close to 2 or negative 2, what's the bottom getting really close to? Because at 2 or negative 2, the bottom is 0, right? That's why we're saying we can't use them. But can't I use 1.99999? Or for that matter, 2.00001? So can you imagine, what is, if I plug in x equal to 2.001, what would the bottom become then? That would be 2.001 squared minus 4. Somebody try that out in your calculator. What do you get? So I cannot use 2, but I can use things really close to 2.
Negative 3.999. 984.
4.0040001.
I have point
Minus
0,
4.
yeah.
Point 004.
It's .004.
Blah, 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 yeah.
Yeah.
So if I use 2.0001, get even closer to 2, do you see what I mean by closer to 2? So here's the interesting thing. We're not going to do a lot with this, and I want to at least tell you the word that's associated with this idea. Some of you guys have heard this before. But it becomes huge in pre-calculus, right? If any of you guys are going into pre-calculus, you're going to be doing crazy amounts of graph analysis. So one thing you're going to look at is this thing. What happens at weird-ass points? You're going to step really close. I always like to think of it when I'm teaching my students, something freaky happens right there. What are you going to do? You're going to do this. Oh. Right? Or at least in a horror movie. You know, don't do it! Right? Some freaky's there, you're going to get close and look at it. So that's what we're doing. We're getting really freaking close to the weird-ass point to see what the hell is it doing. If you try this, it's going to be even smaller. Right? So if you take a number divided by something really tiny, what comes out? Something really large. Because if you do 4 divided by 10, that's 0.4. 4 divided by 1, that's 4. 4 divided by 0.1, that's 40. And it just gets bigger and bigger and bigger. So on the graph, at 2, the idea is what should happen then is it's like a wall. If I plot points, 2.001, 2.001, you just keep getting bigger and bigger and bigger. And to tell you honestly, it's going to be down here because the top is going to be negative. But that's the idea. It's got to slam up against that wall. So let's take a step back. At 2 and negative 2, it can't possibly go through there. Because what did we just say? X cannot be 2 or negative 2. So the funky thing that happens is it slams up against it. I always think about it like, well, here's my true geekiness. They come out and the Death Star still has this shield on or something. You know, and they gotta go, holy shit. You know, they don't want to hit the shield or they're dead. So they kind of do this whole thing. Anyway, that was incredibly geeky. Sorry. But let's just look at the graph on the calculator real quick. Just to see if it does when I said it should. Yeah, some of you guys should be there already if you've tried to graph it.
Well, wondering is how does it get to the other side anyway? If you can't
Well,
get
I can't plug a 2 in, but I can plug stuff on this side in, and I can plug stuff on this side in.
okay, so like
Right, but there's still a separation.
There's a separation, sure.
Gotcha.
Yeah.
But it could be a billionth of a second.
So remind me real quick, how many of you guys are going on the pre-calculus? I think I've asked that a few times. Anybody? Okay, a few of you guys. If you're not, you're going to have to know it up to a point for me. But it's nice to get a preview of it because trust me. I don't want to scare you, but pre-calculus I call it graphing hell because once you come out of there, you should be able to handle graphing from anything because you're just going to really analyze these graphs a lot. So I'm not making it sound great, but that's what pre-calculus is. It gets you ready for anything after that, dealing with graphing. Yeah?
This is exponential growth, right?
Not quite. It's not exponential growth. It looks like it.
Well, I mean, it can be a growth
Or a decay, but it's, I mean, polynomials in general do this, right? Exponential does this kind of thing. And it grows quickest amongst most functions, right? But this just happened, yeah, just happens to go down pretty quickly. Yeah, it's not really exponential. Let's try to plug this in. Now, here's where you gotta be careful. I don't know if some of you guys plugged it in and you're freaked out about what you saw. Don't I have a top and a bottom here on my function? Who remembers what I've got to do for my calculator to help it out since it doesn't have eyeballs like I do? Yeah, exactly. I've got to put it in like this. Here's the top, here's the bottom. If you don't, it's only going to divide 3 by x squared. Right? It knows order operations, but it can't see big division signs. So I'm going to clear this old one out. Here's the top. What was it, x minus 3? No, x. Yeah, okay. That's the top divided by the bottom. X squared minus 4. Alright, so I got my funky ass window going on, right? Let's just try to hit zoom 6. zoom 6. It looks like a heart monitor thing, right? Let me make it a big screen here. Now, this here is the calculator freaking the hell out. It's trying to connect the dots. So this goes down forever. Like we were saying. Over here, look what it does. Well, this side, you can't really see it too well at all, but it goes down forever. So do you see how it's having problems at exactly where we said it would? At 2 and -2. And it's slamming up. Do you see how this one's slamming up against that wall? This one's slamming up against that wall? Does anybody know what that's called if you have something that can approach it but never get there? Certain word for it mathematically. Starts with the letter A. Asymptote. So an asymptote is something you can approach it, but you get closer and closer and closer, but you never get there. And some of you guys might, how do you do that? Well, if you're this far away, cut your distance in half. Cut it in half again. Cut it in half again. Cut it in half. Will you ever get to my arm then? No, because you're always some distance away, right? Yeah.
Yeah, mine looks a little.
Do you not have the little lines?
Mine just goes down and then it has a thing that goes up.
It has 2 parabolas.
Yeah, it has 2 different things.
Did you put this in like this?
Yeah.
Yes. It still has like the split, but it doesn't have the line going all the way up. It's got-
Oh yeah, you're right.
It's kinda
This
like it just had the parabola.
this emulator is acting like it's got very little memory. It's not able to resolve it too well. Let me see if I can make this a little better.
Mine looks just like yours.
This should be like a parabola here. So we got it set on something freaky. No, I don't. This right here should be parabolic right here. Let me zoom in a little bit. I can make it a little better here. Let me see if I can get this a little better.
And mine looks like yours though.
Sorry guys. Let me see if I can make this a little better. See, there's the parabola you're talking about, right? It just has trouble with resolution when it gets really close to that line. It's easy to lose it. And at some point it kind of gives up and jumps down to the negative stuff, right? So what's really freaking this calculator out, and I really don't want to make a huge deal of this right now, but is the fact that this is going to where? Where is this going?
Straight down.
Negative infinity. It's not straight. It's always getting closer to this line. This is what freaks us out. It's always got room. If it's 0.5 millimeters away, it can get half closer. It can get half closer. It can get half closer forever. So it's going not quite straight down, but almost straight down to negative infinity. This side is going to positive infinity. So the calculator is like, shit, right there saying, it wants me to go there and there. Okay? And that's why I got this extra. Some of you guys might not have this extra line here. This is not really part of the graph. That's the calculator going, shit, trying to connect points. So this emulator on the computer is not as good as a real TI-84 should be. Really, it shouldn't have this line there. But if you do, then you got the same trouble as mine does.
Mine has broken line. It has.
Oh yeah, so you're set. You can change the mode here.
Like it has 2 lines going up.
So if let me see if I remember here. If I turn off my, oh no. Where is it? Here it is. See where it says connected? So if you go to mode, see where it says connected?
Mode. And then connected.
Make it dot. And then you get this. Let me bring it back to normal. That's even worse actually, but it's not trying to connect the dots now. It's just trying to put a dot for every point it calculates. Right? Okay, so what's the main thing I want you to get from this? When you see them say, find the asymptotes, that's just another way of saying, what's your domain, right? But you don't say not equal to now. So for example, here, if it said, what's the domain, I would say x can't be this. If it said, where are your asymptotes, I would say there's an asymptote at x equal to 2 and at x equal to negative 2. So this is really kind of interesting. The function cannot be here. So graphically, what does it do? It sets up walls. It says, do not go here. And so what does it do as it gets closer? It slams up against it. It might slam up against it down, or it might slam up against it up. It's kind of nifty. What the hell would happen at a point you're not allowed to go to? Graphically, we see it slams up against it, doesn't get there. So, again, that's when you see the word asymptote, it's directly related to the domain. X can't be this, so where do you set up the walls at 2 and -2? There's another word for asymptote. You can say set up the walls. Where would you put the walls? Yeah.
I have a graphing program.
And does it look pretty good?
It's pretty interesting. And I just tried to zoom it a little.
Oh, freaky. All right. Cool. All right. So, for example, look at on page 451, number 85 through 92. They say determine the vertical asymptotes, right? So really, you just kind of find the domain and then say it like this. That's where the walls would have to go to say you can't go here. 451, starting at number 85. So like number 85. Look at number 85.
Wouldn't you rather do 86?
No, I'd rather you do 86. I like that. What would the domain be for this function? What's the domain? Dominic?
Not equal 5.
Yeah, because
Or
if you
negative five.
factor this bottom, you get that, or if you just set it equal to 0, right? You can solve for it. X can't be -5. So where are the asymptotes or tote?
5 and -5.
Careful. Yeah, there's an asymptote at x equal to -5. Is 5 a problem?
No.
No, so there shouldn't be an asymptote there.
Okay.
Asymptotes are the walls that it sets up at the problem points. It says you cannot go here, so you got to do something else, right? You got to go. I'm coming. Oh shit! And you pull up, or you got to pull down. Hopefully, that's gonna get that. If you don't quite understand this whole idea of stepping in closer, like we did with the 2.01 and the 2.01 and all this stuff, all you really got to realize is this: when they say find the asymptote, it's related to finding the domain. It's really the same thing. It's just where I've got to set up. You can't go here. So where can I go at x equal -5? Can't go there.
So we would write it as a plus x equals -5.
No.
No.
Is that 18?
Yeah.
How fast, okay.
Just looking at that too, like, where'd you get A?
I don't know why they do the T like that. Normally I do my T's like this automatically, just to make it different from my pluses. But yeah, at x equal -5, that's where there's an asymptote, right?
Okay.
And is that domain?
It's related to domain, right?
Right, but how,
Asymptotes exist in relation to what the domain is. So I don't need an asymptote where I'm allowed to go. But if I'm not allowed to go somewhere, an asymptote will be set up there. Okay, cool. And of course there are some special cases that mess with it, but I'm going to leave that for pre-calc. For us, this is the idea. Right? There are very special cases that might happen where something is true, but okay. Someone else set you out there and have a word that you didn't know what it meant. I don't think, yeah, we didn't actually do any of this here, but let me see what you guys think about this. This is 6.2, by the way.
is that from the book, for example?
It's just me hoping that my brain is working to make this do what I want it to do. But the main thing here, I made it do a certain thing, but that doesn't really matter yet. The main thing here is I'm trying to add two fractions, so what do I need?
Common denominator.
Exactly. It doesn't matter, again, x is just a number I don't know yet, so x plus 3 is some number. So it should act like any other fraction does. It needs an LCD. It has an LCD, kick ass, so what am I allowed to do?
Add them up.
Add them up, so I get 4x plus 3 minus 3x over
X
x plus 3. Not x plus 3 squared, right? It's over the common denominator. I always get people try to combine. Oh, they get 2x plus 6. That's neat. This is saying 1/9 plus 1/9 is 2 over 18. Which is 1/9. That's a neat thing to say. Right? So the same thing that happens with regular numbers happens here. Now what's the next thing I can do, obviously?
Combine like that.
Exactly. I like it. So 4x minus 3x. And just like any fraction, the very last thing I do is see if it reduces. That would just be 1. Careful. Something divided by itself is 1. In the background of every problem you do that has rational expressions, there's the understanding that x can't be certain things possibly. In this case, x can't be -3. So everything we just did is not applicable if x happens to be -3. The answer is not 1 if x is -3. But the answer is undefined. How are we doing there? Is that cool? Okay. So how do they get worse? Well, very obviously, the easiest way to make this worse is to make the denominators not like. That's when things kind of suck. I tried to set us up for this earlier in the class. I tried to set us up with fractions to help us when we got to this point. So let's see how this works. Say this. Oh, sorry. Don't put the x there. Okay. Let's put the x here. Yeah. I like it. Cool. So see if you guys remember, I think I gave this example for ugly denominators. A really nice way to handle them is to try to factor and see who's missing what. So that's exactly what we do here, right? Why is this problem here easy if I have 1/3 plus 1/9? Why is that easy? Because who's missing what?
3.
Because we know 9 is 3 times 3. So we know that this guy's missing a 3. Here, I don't know. I can't just look at that and go, oh yeah, that's this, so he's missing that. No, I can't do that. I've got to take a second and say, what the hell is he? And then I can see what the hell is he missing. So what the hell is he? I like it. So what's he missing?
X plus 6.
So you give him what he's missing. Just like you would do here. Now I keep going back and forth on how to teach this because there are mistakes you can make both ways. So let's just see what I do. I think I'll do this. What do you get up here? Plus 2x, because now I can combine them because you've made the bottoms the same, right? Once you make the bottoms the same, you're allowed to combine them, right? That's the whole idea. If I can get like denominators, I can add fractions. What do you get on the bottom?
X squared plus x.
Yeah. If I have so many x plus 8 over x minus 7s, plus so many x plus 8 x minus 7s, I get so many x plus 8 x minus 7s. Right? The bottom doesn't change. And then you can get your like terms together, right? So it's really interesting. Factor, give everybody who's missing something what they're missing. Combine, clean up. So we're at the cleanup stage. So 3x and 2x. Now real quick, if I had written this like this, it's really the same thing, right? What mistake do you think people would make?
Cancel.
Yeah, they'd say, oh yeah, but that division can't break into an addition problem. But if you write it like that, you think, oh cool. But then it's like undoing what you did to make it legal, so what the hell? So that's why I'm thinking maybe better not to write like that. Maybe better to simplify on the way, so you don't make that mistake.
Or you're supposed to distribute that first anyway, right? Because multiplication before addition.
But you can just rewrite the problem, and then you can distribute.
I see.
But then people, if they rewrite the problem, they think, oh, cool, this goes away.
Because you're not really doing anything, you're just putting them next to each other.
Yeah, exactly. Just not yet. Just rewriting what I got so far. Do you guys get the feel for this? I mean, it's almost, on one level, it almost seems too easy. You're like, just factor and give the people what they're missing. Just give them what they're missing. Just give it to them, and then just combine the help, right? It's really not that bad as long as you're able to factor. Again, if you can't factor, it ain't gonna happen. What about this one here?